This is topic 1, testing a claim on the relationship between two categorical variables, which is our first topic in Unit 5. So as an introduction to Unit 5, in Unit 4, we had done a majority of the traditional hypothesis tests. And in this unit, we did 7 steps, and every single hypothesis test operated under the same concept, but we just needed to change in whatever we are testing exactly for. So whether we're testing for a mean, proportion, or a standard deviation. And then my next question is usually whether it's one population or two populations. Well, we have 4 topics remaining in our last unit, and there's not an exam for this one. It's going to be guaranteed that we'll have one of each of these problems on the final exam since we don't have an exam on it. So what we do in this last unit is we look at some of the less traditional hypothesis tests. So this first one is kind of similar to the last ones, but with some changes made in. This one is almost identical to some of the Unit 4 problems. And then this one is kind of in the middle. Correlation and regression has some similarities, but it is kind of its own topic. So again, we're still going to follow the same 7 steps for hypothesis testing. We're going to be operating under the same concept with comparing our p-value to whatever our alpha is, but there is going to be some more unique aspects to these non-traditional hypothesis tests. So first we have a new hypothesis test reference tables. For your final exam, you will get all of your reference tables, except for the confidence interval ones, because we won't be doing those by hand any longer. So this first one is our confidence interval, our reference tables for topic 1, testing a relationship for two categorical variables. And so I'm going to go through this in general, but there is going to be a few pieces that we'll go through a little bit more specifically with the notes. So our HO, I always remember that HO is no, and HO is no relationship between the two categorical variables. And your H1, the alternative hypothesis, is that there is a relationship between variables. Our assumption, we want a random sample, but again, in reality, this can't always pass even if we want it to. And then this seems like it's really different at first, but it does kind of have a similarity to the proportion assumptions. So if we remember the assumptions for the 1 and 2 population proportions, that there had to be at least 5 successes and 5 failures for each population. Well, in this one, we need an expected count in each cell or expected frequency to be at least 5. So I have a grammar issue here. So that's pretty similar in some ways, but it is different, and it will feel different because it is a little bit different. This is the test statistic, just an FYI. We will not be finding this by hand. One of the ones we will find by hand later on in this unit, but this isn't something I could do this by hand, but I haven't in a very long time, and I'd really have to think about it. And then the theta is going to be the biggest thing that differs. So tab chi is going to be our theta command. It's going to have a slash at the end of each row and comma adjust. So all of these 3 things are new. So that there's going to be special instructions on. And then our post hoc test, this is the largest thing that is different between the Unit 4 and Unit 5 hypothesis tests. So we'll get into that in just a second. First, I wanted to show you that there is an individual instruction sheet for how to do this test in Stata. So, if you are, maybe having a hard time following along and pausing the video isn't doing that great, there is this sheet here which has the individual instructions. So this is here for you. But let's get into it here. I like this test a lot. I find it to be pretty interesting, even though I'm really more of a numeric person. So I want my output to be, heights and temperatures and stuff like that that's on a number line. I do find categorical data interesting, but it's just in general not the type of thing that, I'm usually asked to do in the real world with stats outside of teaching. But a lot of you guys, categorical data will be a little bit more in your area that you'll need to address when you're in your professional setting. So, just as a reminder, categorical variables are things that are, yes or no. It could be Democrat, Republican, Independent. It could be, the highest degree that you've completed. So it is things that doesn't have a numeric response. So yes or no, win or lose. So our assumptions, or I'm sorry, our hypotheses are again going to be HO is no relationship, and H1 is that there is a relationship. This talks about our assumptions. And then this is something that I would definitely have down on your note sheet, is that our step 7 is very different. So previously in unit 4, our step 7 was always a confidence interval. And for one population test, it was confidence intervals on a population value. And for the two population tests, it was a confidence interval on the difference between the two population values. Well, this is going to feel a little similar to something that we did in Unit 1, and it works, but it's not as similar as it seems just in its, original sense. But it's still a good tool to use to help you learn it. So when we get an output for this, it's not a confidence interval. It's going to be a table with what's called adjusted residuals. And the way that we interpret the adjusted residuals are if they're close to 0 or very close, then we are getting the amount in that cell than we expect. So I know this is very vague right now, but the more that you pick up before we go into the problem, the easier it will be to start that type of problem. So if the adjusted residual is less than -2, the count in that cell is less than expected. And if it's more than 2, the count in that cell is more than expected. So basically the way that we are going to characterize this is pretty similar to our rule for standard deviations. So originally we have, all right, -2 is one of our cutoffs, 0 and 2. So if your adjusted residual is outside of -2 or +2, then we're going to say that we get a different amount than we expected. So lower than -2, less than expected. If it's in between 0, -2 and 2, then it's about what was expected. And then if it's outside of +2, then we'd say it's more than expected. So this again is very vague right now, but this is going to be kind of our guide as to interpreting our step 7. So this is something that I would, have written down right now and refer to when we look at our first two problems. So all of this is real data. The second example is really a lot, more straightforward to kind of feel and understand what the problem is testing, but it's also more complicated. So I decided to look at a slightly calmer version. So the following data is from the paper Gender Differences in Food Selection of Students. It's the result of a random sample of 139 students whom were first classified by gender and then asked whether they usually or rarely eat 3 meals a day. At the 0.05 level, can we say there is a relationship between gender and eating 3 meals a day? So first of all, because this is only 2 by 2, we could actually do a 2 population proportion test on this data. But we would be sort of saying we'd end up with a similar solution just expressed in a different way. So what this table is this called a contingency table because it has whether or not they eat 3 meals a day or they rarely eat 3 meals a day contingent to their gender. So when I'm eyeballing this one, I see, okay, I have the biggest number here, but there's also more females that participated. So when the test is ran, you can't just, look at the numbers at face value. You have to kind of say, okay, this can't be taken at face value, but in general, so these seem pretty even because, there's an equal number of each of these. Okay, so for the females, there's an equal number of each of these, but the table also works vertically as well. So I like to understand my table really well, but I don't usually read too far into it because it gets way more complicated. So having an instinct is helpful, but you have to be willing to understand that the instinct alone isn't going to be good enough, which is true in general of hypothesis testing. So these are also calculator. So you're going to look at the one. Oops, so we don't have a Stata one here. So this is if you did it in the calculator. And it's much, much better to do it in Stata, believe me. So HO is no relationship between gender and eating 3 meals a day, and H1 is that there is a relationship. So notice that there's not an official stated claim, and part of this is because regardless of what your claim is, you're going to have the same HO and H1. And the other reason is that we've talked about how you don't usually want your claim to be HO because we never say HO is true. We just don't get rid of it at the time. So I set up my same 7 steps, except for there's no picture. That's kind of nice. And the reason is we could totally do a picture for this, but the pictures in Unit 4 help us understand the way that hypothesis testing works. And I don't feel that the picture for this topic does that. I actually think it makes it a little bit more complicated. So for that reason, we're not going to do a picture. I also wouldn't do a picture in a professional capacity if I was presenting anything, but I would probably, at least visualize the picture in my head. So we can pass random right now, but we can't pass this assumption yet. We'll get to that in Stata. So this assumption, you have to remember to come back to it. The chi-square value, we'll get that, but I always do chi-square equals p-value alpha. And so then when I come back to the problem, I can just write in, everything that I get from Stata. So this now brings us to the Stata aspect of this. So the first thing is that Stata doesn't come built in with this command. So what you need to do is have it find it. So you need to have an internet connection in order for this to work. And I'm going to, just because I'm sure this probably, it's hard to tell because I have a very large computer screen. So if you type find it, and then the command is tab chi. Now notice when I type this in Word, it automatically did a capitalization. You cannot have a capitalization here. It's very, very picky because it's basically working the way a programming language does. So tab chi is what you want to have it find, and you only need to do this one time. So find it, tab chi, and then it has a pop-up window come open. So the first link is the one that you want to click on. And when you do this, it pops up with a secondary window. And then, my computer, it's already downloaded it, but depending on the speed of your internet connection, it could take up to maybe 10 seconds, but it shouldn't take any longer than that. So once this screen basically pops open, it should be done with its download. And then, or it should be ready to download. And then you click here to install, and then it's downloaded. So I already had mine installed, but that's okay. So what it does is it just checks to see if you have it, which you wouldn't at your home computer. The school computer should have it on any of the computers if you do come in to work in the stat lab or something like that. Once that has downloaded, you just click the X. So after that, you are all set up to put in your chi-square test. And so so mine is going to look a little bit different than yours because I closed out of my one of my viewers here. So if you have a menu on the left side or right side, that's totally normal. So the data we want to enter in is going to be this table, and we're going to enter it in by row. So when we use this command, we're going to put, so tab chi, we're going to again say, hey, this is the command that we want to use now before we taught it to Stata. And then you enter in the data by row. So I'm going to do 26 space 22, and then you need to do a /. It needs to be the slash that is in this direction. So this is above the enter key. If you do the slash the other way, it's not going to work. I'll show you what that error looks like because, you know, it might be something like you might not notice the slashes a different way just because to you it's a slash. But to Stata, it's a programming thing and it's very picky. So 26, 22, 37, 54, comma, adjust. Perfect. So then you're going to go enter this into Stata. And so then it gives you back a table and some other stuff and a description. So let me just show you if you put the slash the other way, which is the normal way you're used to making the slash. It says that a slash is found where an integer is expected. So it's expecting either a number here or a slash that's in the correct direction to indicate that the row is done. So now interpreting the table here. So what it gives you is it gives you back a table version of what you've already entered in with some other stuff in it. So notice that we had a 2 by 2 table. And so when we go to the Stata output, which this is in Paint, which is why I'm able to do all this modifying to it. When you go to the table version of it, it's a 2 by 2, but it's got a lot of other stuff going on. So the observed frequency is what the sample data found, and it's giving that back to you. So this is an opportunity to make sure you've entered it in correctly. So then the expected frequency, oops, let me pick a color that's a little bit more different. Let's see, not green. All right, there we go. Expected frequency is if every one of these was equally likely to happen. So it didn't matter whether you were male or female, you were equally likely to eat 3 meals a day or rarely eat 3 meals a day at the same percentage, or the same amount at this case. So we expected 22 if there was no relationship at all between gender and eating 3 meals, and we got 26. So, I mean, 22 and 26 aren't very big numbers. If somebody owed you $26 and they gave you 22, depending, you know, that could be, you know, a grounds to say, hey, you need to give me more money, or you may just let it go. So we'll talk about, you know, the weighting of that, how far is too far. We expected 26 here, and we got 22, so those are flip-flopped in this case. So that's off by a similar amount, by about 4. So this one was 4 less than we had expected, if we assumed there to be no relationship at all. So for females, for usually eating 3 meals a day, we expected 41 and we got 37. So that's off by the same amount. And then for females, for rarely eating 3 meals a day, we expected 50 and we got 54. So because this is a 2 by 2 table, there's only 2 rows and 2 columns, there is going to be a lot of flip-flops here. So for example, oops, let's make that blue again. The adjusted residual then tells you, okay, based on the sample size, this is how much of a big deal this difference is. So the adjusted residuals is what we interpreted on that number line that we had here previously. So that's understanding this output table. The p-value and the chi-square value that we get are always going to be the first one up here. So the chi-square value is 2.31, the p-value is 0.1282, so it's off by just a tiny bit. So this is because of maybe the difference of the software that I had used when I calculated this. The p-value is higher than whatever alpha is, which was 0.05. So the HO will fly, so we're going to fail to reject it. And then what that means is that we conclude that there is no relationship between gender and eating 3 meals a day. So we failed to reject HO, and HO is no relationship. Now, the other thing is that we didn't pass or fail this assumption right here. If this assumption fails, it is absolutely game over. So the normality assumption, depending on how bad it fails, sometimes, you know, you can justify running the test anyway if you have some other stuff to back that up. But so 21.7, 26.2, 41.2, and 49.8. So that value, so I had actually done this in the calculator, which uses slightly less accuracy. So these are the values that you should expect. So now for your step 7, the adjusted residuals, I always put this down. So 1.5, negative 1.5, negative 1.5, positive 1.5. And again, since there is a 2 by 2 table, there's only pairs in each row and column, these are going to be flip-flops. So since all the adjusted residuals are between negative 2 and 2, this supports that there is no relationship between gender and eating 3 meals a day. So these are not too far away. They're not greater than 2 or less than negative 2. So this supports failing to reject HO. So the next problem, I think, again, is a little bit more relatable. However, one of the problems with it is that it is a little bit more complicated. So now we have a 3 by 3 table. The tables don't need to be square. They just need to have, a number filled in for each level. So a level is liberal, moderate, conservative in this case, and Democrat, independent, Republican. So these are levels of the political party. So the General Social Survey of the United States asked people to describe their political ideology and whether they think of themselves as a Republican, Democrat, or Independent. The results are below. Does there appear to be a relationship between ideology and party? So just as a person that lives in the United States, so that's only these are only people in the U.S. So that's why I say as a person that lives in the U.S. If you were asked, do you think there's a relationship between whether or not you're a Democrat, Republican, or independent, and whether or not you identify as liberal, moderate, or conservative, do you think there's a relationship between those? And I think most people would probably say yes. So I think a liberal Republican is probably something that I hear of less frequently. I have no idea what these independents are going to do. I have no idea if they're independent because they don't want to pick a party or they identify with, a different party than these two. So I have no idea the reason for that being, the identification. So I have no idea what's going to happen here. But I'm guessing that there's probably going to be less conservative Democrats. But, it is something that you kind of hear, like, oh, I'm, conservative fiscally and Democrat socially. So that's something that, you could hear from somebody more often. So I think this is going to be unusual, but not incredibly unusual. I don't know. So I usually just like to say, what do I expect from this? Because I'm always going to give you real data. It always should be something where, your own personal knowledge can kind of play a little bit of a role. But the p-value is ultimately the tell-all. So our HO is that there is no relationship between party and ideology, which I think that should fail. And then our H1 is that there is a relationship between party and ideology. So this is as far as we can get before we get something from Stata. So our random assumption fails. However, the General Social Survey is usually a pretty comprehensive, and they try really hard to be as representative as possible. So this is a case where, no, they can't actually, do a random sample of everyone in the United States, but they've still tried really hard to make it be representative, even if it's not exactly a random sample. So I'm going to window this over here, make it a little smaller. So when I enter this into Stata, I'm going to use the tab chi command, and I'm going to have each row, and you have to do it by row because remember the output gives you the same exact table back. So this should be what you are entering into Stata, into the command box. So our rows, I'm just going to double check this. Okay, and then comma adjust. So when you hit enter, it again gives you a table back, but with more information. So the first thing I want to know is, okay, I feel like I should be rejecting HO. And so that's what this says here. 325.22 is our test statistic, which is a really big chi-score value. I know at this point it's not something that you might have a good feel for because every single sample size is different, but this is pretty big. And our p-value is 0 plus. So it's not actually 0, but it's just going to round to 0. So then our expected, let's just finish checking our assumption before we forget. It's very easy to forget to check this assumption. I do it at least half the time, and I'm pretty aware that I know I can forget it. So actually, and I forgot it in my upload. Yep. So I swear I didn't do this on purpose, but our expected is the second column. So if you forget that, it tells you up here. So the expected is the second value in each cell. So our lowest expected value, I think happens in the bottom left, is 176, which is pretty low, or I mean pretty high. So it's way far away from 5, so we are able to pass this assumption. So we talked about our chi-square and p-value. The p-value is low, we're going to reject HO, and then we conclude that there is a relationship between party and ideology. So I actually recommend rounding to more digits than I had rounded originally because it could eventually end up causing problems if your cutoff is really close to 2 or -2. But so notice that I recopied this table. So 8.0, 3.1, -10.6. Okay, so 1.14. So I've just copied the bottom row of each of these. And so this is what's basically saying, you know, this is my confidence interval. And it's this version of the test, or sorry, this non-traditional test. So 9.9, -7.7, and 17.2. So these are your adjusted residuals, and so after that we don't really need theta anymore. So the way that we interpret this is that the farther away the number is from -2 or 2, the more extreme it is, so the way more or less what we had in that cell than expected. So this top row is Democrats, this is Independents, and this is Republicans. So Democrats were more likely to be liberal. Okay, 8 is way bigger than 2. They are slightly more likely to be moderate, and I just, you know, it's not formal, but it's bigger than 2, but it's not way bigger than 2. And then they are less likely to be conservative. If it's in between 2 and -2, you don't need to interpret it per se, because usually you just want to know, hey, you know, what's wild, what's different than what we assumed. So the independents were slightly more likely to be moderate and decently less likely to be conservative. And then Republicans were way less likely to be liberal, way less likely, I would say again, to be moderate, and way, way, way more likely to be conservative. So I did put a note where liberal independents were within a normal range, and that's a normal range assuming that their independents were equally likely to be the same for each. So that's one reason why I don't usually interpret ones that are in between -2 and 2, because they, you know, they're usually not as easy to understand without a comparison, which is showing what other things were different than what we'd expected if we assumed that they were all equally as likely. So I'm going to leave this last problem for you guys. This is definitely one that you should check out on your own. I recommend as much as you can, do not look at the answer key before you've done your before you've ran your test. So try it first. Getting it wrong and correcting it is actually the best way to learn, although nobody likes getting the problem wrong. And as always, if you have any questions at all, please send me an email.